in the process of doing confidence intervals, which is what we're doing, I described for you how confidence intervals are, to some extent, quote unquote, the method for doing statistics. Can somebody tell me the purpose of the confidence interval? What does the confidence interval do?
It's used to give measurement for a population.
Okay, what we're doing here is we're used to get a measure of the population. And we put a star around that because the confidence interval, though it comes from a sample, gives us information about the population. That is the process of statistics that we want to use. And if we're able to do that, then our idea of what to expect makes sense, because I don't just want to know what I can expect from my sample. I want to know what can I expect in reference to my population. Now, specifically then, we covered doing confidence intervals for the proportion. But now we want to talk about the mean, and then later we want to talk about standard deviation. For the mean, I want to know what is the symbol for the sample mean, and what is the symbol for the population mean. Can someone tell me those things? If I have a sample mean, I'm going to use the symbol x bar, and population mean mu. Greek letter mu. Okay, so those are my symbols. And when I do this, we had talked about how I have certain requirements that would allow me to say that something is bell-shaped. And so if I'm looking at my sample mean and I want to say, how can that be bell-shaped? Those ideas are important, except for a problem that when I want to use the central limit theorem, the central limit theorem requires knowing the population standard deviation. What's the symbol for the population standard deviation? Standard deviation for the population is? It is, but we have a name for it, which is sigma. Okay, it's a small sigma. And so when we think about, can I get a confidence interval for the mean using the central limit theorem, which says bell-shaped? The answer is no. I can't use that because I don't know sigma. I don't know the population standard deviation. So I want to use, okay, I want to use the sample standard deviation. What is the symbol for the sample standard deviation? It's just S. Okay. So I want to be able to create a formula that will help me to predict the mean, but I don't have the mathematics from the central limit theorem. It won't work to make it bell-shaped. So then this guy, William Gossett, came up with the idea, and because of his employer, he had to use the false name student. So this is called student's t-distribution. Student's t. So that means we're not going to have bell-shaped data, but it's going to have a lot of the same characteristics. And so when we look at the question of what that looks like, then in your textbook, it has a picture of that, which is on page 438. It looks a lot like the bell-shaped normal distribution. However, the mathematics are a little bit different, and so it creates a difference in the tail sections. And as you may recall, when we're talking about a confidence interval, we want to know how to get those numbers. How wide does this thing have to be? How far from the left to the right? We would have the mean here in the middle, and then we want to know how accurate we can be for our interval. And so then, using the student's t-distribution allows us to do the sample with the sample standard deviation, and it gives us close enough what we want, right? Once again, all of this is just in terms of experience, people who have done statistics, who have used these numbers, that have been able to figure out things based on random selection without any confounding variables, and these numbers are constantly changing and all that other stuff, okay? So we cannot actually say that we know things for sure using a confidence interval, but it's a reasonable hypothesis. It's a reasonable idea of where to look. And so then, if we use this student's t-distribution, then that's going to require us to use some kind of technology to figure out what these numbers are. Now, one possible thing that we can use for technology would be to use the table, which is in the textbook. And if you use the table in the textbook, then we're going to be looking at what is the area in the right tail. So, for example, if I want a 95% confidence interval, then that means it's 95% in the center section. I'm going to have to consider what is the opposite of that. What symbol do I use for the opposite of confidence? Well, it's the letter alpha. Alpha is our chance of being wrong, and so that would be for a 95% confidence interval, 0.05. And then when we're doing the distribution here, we have to split it in half, alpha divided by 2, which is 0.025. So then when we look up on the table, we see I have an area in the right tail of 0.025. And then in addition to that, in using the t-distribution, I have degrees of freedom, which is n-1. Now, it's just how this works, okay? In a statistics textbook, why do they require you to take n-1? Why couldn't they just use n in the table so you wouldn't have to remember it's n-1? Because they just think about things in their formulas. They don't think about what makes it easy to look up. So then you have to put in degrees of freedom, n-1, instead of just looking up the thing you want. So we look up degrees of freedom. That tells us what row is on the table. And then the area in the tail is the column that we're going to use. And so when you look at that table, you can see how you can find out the t value. And just as with the proportion, that's where the formula comes in. That the confidence interval for the mean is x bar minus t of alpha over 2 multiplied by s over square root of n. That's the left side. And on the right side, it's plus. Now, I put this formula up here. The fact of the matter is you don't need to know it. Because if you use StatCrunch or some other software, you don't have to do any of this calculation. You can just put into your calculator or your computer, this is the sample mean, the sample standard deviation, this is my amount of confidence, what's the confidence interval? Boom, there it is. And that's fine. I don't mind you doing that at all. If you want to use the formula, look things up on the table, put all the numbers in, use your calculator to compute it, that's okay. I would recommend that you not. I would recommend that you just use the software that's out there in order to use this confidence interval. And the t-scores that you're given on the table, those are actually rounded off, right, to 3 decimal places. You could use Excel or some other thing and get the t-scores to 20 decimal places. So the table is not like a sacred book of some kind. You can use a calculator or computer to find t values and have them more accurate and do it that way. That's okay. I'm giving this to you so you can see how it works, right? And so that you can see that it's the same concept as what we talked about with the central limit theorem, but we have to use t instead of z based on the fact that we don't know the standard deviation. So this process, taking this through to make it work for the confidence interval for the mean, once again, our goal is to locate the population mean. I would like to know what are the reasonable values that I could consider for the population mean. And I use this interval to try to find it. The interval could be wrong, but 95% of the time, I'm confident that this actual value of the population mean is somewhere in between these two numbers. All right, so what questions might you have about confidence interval for the mean? Anything out there? All right. So now we want to do a similar kind of a thing, but we want to do it for the standard deviation. So now things are substantially different. I am going to look for, I want to find an interval for sigma, population standard deviation, based on S, the sample standard deviation. And I want to make that work. As it turns out, in this situation and the one previously, and I'm sorry I forgot to mention this, but in both of these situations, this will work if we have bell-shaped data in our population to begin with. The mathematical processes that we're going through right here require us to have bell-shaped data. And the fact of the matter is we don't know necessarily if our population is bell-shaped or not. So we just do the best we can. We kind of make some assumptions, say it's probably close to bell-shaped. If I have a large enough sample, maybe I can look at it and say, well, is the sample bell-shaped? Maybe the population's bell-shaped. We can go through that process. We're not going to focus on that, even though your textbook does go through that in the homework sometimes. They'll say, okay, here's information about the sample. Do we think the population's bell-shaped? And we do, then we keep going. Again, this is a matter of experience. If you're doing something where you're the first person who has ever measured this thing, whatever it is, well, then you should probably not assume it's bell-shaped. You probably have to have more advanced measurement process. But if this is something that's similar to what's been done before and you are pretty sure that it is bell-shaped or close enough, then you're like, okay, well, let's work with what we've got. So we're trying to work with this kind of a situation. We're trying to figure out what is the population standard deviation. And what happens here is that we're going to be working with no longer the central limit theorem. We don't have Z and we don't have T. We're going to have to use something else, which is called chi-squared. You might notice there's a lot of Greek letters running around. This is another one. If you've ever gone Christmas shopping, you've had an experience of chi, because chi is actually the first letter in Christmas. Not in English, but in Greek. This is the letter chi. It's not chi or chai or anything. It doesn't have anything to do with yoga or beverages. It is the letter chi. And then we have a square. This is chi-squared. It's not the funny looking X, it's chi, all right? So you say chi-squared, and you sound really intelligent when you say that, chi-squared. So then, when we say, I want a confidence interval, well, it turns out chi-squared is not symmetric. Chi-squared looks like this most of the time. It has a positive skewness to it. So if it's not symmetric, then we're not going to have, as we had before, where we have plus and minus. That's not how it works. Chi-squared uses a very different method to figure out the confidence interval. So then what we have to do is, to a certain extent, on page 451, it'll show you how to come up with the confidence interval. We're not going to worry about that. We're just going to use the formula. But then there's a weird thing that happens on page 452. It says, to find an interval for the standard deviation, you need to take the square root of this formula, or words to that effect. So what I'm going to write up here on the board is actually the confidence interval for the standard deviation. In the textbook, it's giving you the confidence interval for the square of the standard deviation. Once again, it's because they like their formulas more than they like actually explaining things. C'est la vie. So what does the confidence interval for the standard deviation look like? Well, it has the population standard deviation inside, like that, which is what we want. But then, on the left-hand side, it has this. The square root of n minus 1 times s squared over chi-squared of alpha over 2. And then on the right-hand side, it has n minus 1 s squared chi-squared 1 minus alpha over 2. Once again, this is in reference to the table. When we're looking at a table of information, we want to be able to find out these numbers that go into the formula based on the chi-squared distribution. So then, once again, if we have a 95% confidence interval, alpha is 0.05. When you divide by 2, it's 0.025. And then degrees of freedom, once again, the formula changes depending on our size of our sample. So then we have that as well. But just to give you an example, if I had, let's say, n was equal to 10, degrees of freedom was equal to 9. So then if I'm going to use the table for this, then I look up chi-squared values. And if you do get a physical copy of the book, you've got these nice sheets that come with it. But otherwise, it's all in Blackboard under tables and formulas. So you could look there for it. And so then if we have degrees of freedom is equal to 9, if I look up 0.025, then I get this number, 19.023. So that is chi-squared on the right-hand side, 19.023. That's with degrees of freedom 9 and an area to the right of 0.025. Okay, so that would be my number down here, 19.023. But then when we ask the question, what about to the left? Well, it's unfortunate that the table does not say anything about areas to the left. It just says areas to the right. So then what I have to look at is, if this area over to the left was 0.025, then that means all this to the right would be 1 minus that, or 0.975. Once again, if I'm using the table and I look at this, then I have to go with that column of 0.975. Degrees of freedom 9 would be 2.700. So that's this number. .700. Now, how comforting is this? Well, not very comforting, okay, because it seems like it's pretty complicated and it doesn't have to be. Well, that's true. In fact, if you go out onto the resources section and look at the calculators that I have out there from Matt Bognar and University of Iowa, you can just put right-tailed or x is greater than, and then you can change it. X is less than, and you can just make it happen. So you don't have to go through all this analysis. And then, if you're using StatCrunch, and you say, I want to know the confidence interval with standard deviation, you don't have to look up anything. You can just put in the value of the standard deviation, the sample size, your amount of confidence, and it tells you the numbers. However, I think it is good for you to see what the chi-square distribution looks like. So yes, when you create the confidence interval for the standard deviation, you would need to be able to find these chi-squared numbers, chi-squared to the right and chi-squared to the left. And again, if it's chi-squared to the right, that corresponds to just alpha over 2, in this case 0.025. But if it's the other one, and you're looking at this particular table, you would have to do 1 minus 0.025, you have to look up 0.975, and that gives you this number, 2.7. And then you'd put that in the formula and make that happen. So, again, because of technology, not having to know how these things work, you can just put in numbers and get a result. However, I think it's good for you to know the difference between confidence interval for the mean has 0 in the middle and it's just plus or minus, but confidence interval for standard deviation has this more complicated form, and all the square rooting and everything, it all works out, hopefully, to make that work. All right, so we will put an end to our video here.